The search for easier, safe systems programming. This is an article about a new programming language that this person, who is an academic, I'm pretty sure, a professor. I guess we'll see. We'll see. We'll just read the article. How about we read the article? Okay. Then we'll see about the people, because I could be wrong. This happened on May 8th. Right now it's May 27th. Oh, it's my mom's birthday. I really need to call her. I have to remember to call my mom on her birthday. I better remember that. Okay. The search for easier safe systems programming. I've been involved in the Rust project in some form or another since 2016, and it's a language I'm very comfortable using. Many Rust programmers could say the same. But if we take a step back and are honest with ourselves, I don't like to do that, we'd admit that the road to getting to that level of comfort was difficult. Okay, fair. I taught Rust professionally for 2 years. Watching the faces of people trying to learn Rust for the first time reminded me just how hard this language is to learn. After 2 years of that, I wanted to answer a question I wasn't entirely sure had an answer. Is it possible to make an easy to use, easy to learn, and easy to teach safe systems language? So basically, you want Go for systems. So you just want a non-GC'd Go. Could I put my career working on programming languages? TypeScript. Try not to hold that against her. Rust, New Shell, etc. to use and find a solution. Enter June. Why did she not wait until June to announce this? Does anybody else feel like that is a lost opportunity? This article is not talking about JavaScript with types, I promise. It would be really bad if I was wrong. For the last year and a half, the language is not called June. That's why. I thought June was going to be the language, but it's actually a person? No, there's Jane. Okay, nope. Okay, let's just read. For the last year and a half, I and my recently added collaborator, Jane Losari-Lusby, have been working in secret. Wow, stealth mode, on a safe systems language that could be learned about as quickly as one can learn Go. So it is literally what they were trying to do. I think we might have something worth exploring, changing how we think of memory. In Rust, we think of each piece of memory as having its own lifetime. Each of these lifetimes must be tracked, sometimes leading to rather complex code, complex error messages, and or complex mental models of what is happening. The complexity, of course, comes with the benefit of being highly precise about each and every piece of memory and its reclamation. Using a Rust example, we got a node struct with some data, pointers. Rust developers will spot right away that this is an incomplete example because we don't have lifetimes. We need two more things, lifetime parameters and lifetime annotations. Adding those, we get this beautiful piece of work. The concept count for this example ends up being pretty substantial. Counting them off, we get lifetimes, lifetime annotations, lifetime parameters, ownership and borrowing, generics. When I showed examples like this to my class when I taught Rust, I had to walk them through each of those concepts first before I could show the full example. The question then is, can we make this easier? Probably. What if memory was grouped? Arena allocation much? What if instead of having to track every piece of memory's lifetime separately, we let groups of related allocations share a lifetime? Isn't that literally an arena allocation? I don't know. Maybe it works a little differently, but we'll see. Effectively, this would mean that a data structure like a linked list would have a pointer pointing to the head, which has a lifetime. Mm-hmm. And then in every node in the list you can reach from that head has the same lifetime. Yes. There are some benefits to this approach as well as a few drawbacks. Let's take a look at the benefits first. Benefits of grouped allocations. Exploring grouped allocations, we notice some immediate benefits. The first is that we could treat all user-defined values as pointers, and these pointers could also represent their own lifetimes without needing lifetime parameters. This makes the code feel quite a bit lighter. Struct node. I didn't actually let in the sentence I just read. Hold on. All user-defined values as pointers. and these pointers could also represent their own lifetimes without needing parameters. Okay, sure. Okay. So this is basically like how JavaScript works. Like everything's a pointer. Struct node data a64 next node. Let n equals new node data 123 next none. Sure. Since all user data is pointers, we can use the name of the type to mean pointer to this structured data. The next thing we noticed is that both lifetimes and inference for lifetimes become significantly simpler. Let's take a variation of the example above. Struct node data AI64 next node fun do this, let n equals new node data 123 next none. We can infer that the allocation that creates new node has a lifetime in what it is. Because this allocation never escapes the function, any JSON, thanks for the follow. That is, it never leaves the function in any way, then we can call its lifetime local. Sure. As we'll find out, each of the lifetime possibilities is a readable name that we can show the user in error messages. It also makes things significantly easier to teach. Let's look at another example to see a different lifetime. Struct stats, age I64, we've got an employee struct, sure, that references stats. We have set stats, okay, and then we have a little main where we're creating an employee, setting some stats, and printing an age. A bit of a longer example this time, but let's focus on this function, set stats. What's the lifetime of this new stats allocation? I mean, you'd probably set it to the lifetime of employee, which is the argument. Which is essentially, I mean, it's not quite how Rust works, right? Because you have to manually put all this stuff in. Okay, we'll just keep going. In this example, we do see the new pointer escape the function via parameter. We can also give this a readable lifetime, param employee, sure. So all parameters of employee have a certain lifetime. In all, we have 3 lifetimes an allocation can have: local, param, and return. Any data structure you want. Another big advantage of grouping our allocations is that we no longer have to worry about a drop order. This means we can think of the whole thing as dropping all at once. For large structures, that can be a speed up over languages with a required drop order. Sure. Additionally, we get another major benefit. We can now create arbitrary data structures. Okay. And just like that, we've made a circular linked list. Creating a similar example in Rust is certainly more of a challenge. Yeah. It is. So let's see what they actually did. They have a new a node 3, a node 2 that points to 3, and a node 1 that points to 2, right? And then node 3's next is just node 1, right? So circular linked list. Yeah. Creating a similar example in Rust is certainly more of a challenge. Yeah, I mean, essentially you'd have to use RC refcell sort of thing, and I don't know. I've never actually. Let me think. I think that would work. I think it would work. But something fishy is going on here. To make the above work, we're using shared mutable pointers. This is explicitly forbidden in Rust. Why is it okay here? Why are the shared mutable pointers okay here? Yeah. I think I have a guess, but we'll just keep reading. The dangers of shared mutable pointers. Rust, this isn't that long. We're over halfway. Rust disallows holding 2 mutable references to the same memory location, and for good reason. Well, multiple reasons actually. First, having 2 copies of a mutable pointer where 2 separate threads each hold a copy means we have the possibility for a race condition. This can leave us with incoherent data that's difficult to debug. How in the heck can they make them safe? My guess is because, okay, this might not make any sense. should I try to make a guess? And then we'll see how wrong I am. If everything has the same lifetime, no, it has nothing to do with lifetimes, does it? Because that's just about dropping. So why is a circular linked list safe by having these inferred lifetimes? I don't know. Just kidding. I don't have a guess. All right. This can leave us with incoherent data that's difficult to debug. At least I'm not good at coming up with things on the spot. Clone on write. That's a good example. That's a good guess. Maybe everything's a cow. Is it Swift that does that, where everything's a cow? There's a language that makes everything a cow. Something like that. Maybe it's Swift. I can't remember. Yeah. Okay. This can leave us with incoherent data that's difficult to debug. Second, even if these two multiple pointers are limited to the same thread, we get what we might call spooky action at a distance. The modification of one pointer is then visible to the holder of the other pointer, which might be far away from the source of the mutation. For us to reasonably use shared mutable pointers, we need to tame both of these. The first issue, the race condition, is easy enough. We prevent sending shared mutable pointers between threads. This limits them to a single thread. The second issue is decidedly harder. There have been many attempts at ways of handling this through rules enforced by the type system. Okay. Yeah, we prevent sending shared mutable pointers between threads. That's why we have arcmutex and Rust, blah, blah, blah. So this limits them to being single-threaded. Okay. So essentially an RC ref cell situation, but I'm guessing they're going to do something a little different. What was the second issue? I already forgot. The modification of one pointer is then visible to the holder of the other pointer, which might be far away from the source of the mutation. Okay. In June, we're trying something. It is called June, and they really should have released it in June. They should have announced it in June. What were they thinking? In June, we're trying something a bit different. We'll let developers use shared mutable pointers, but then offer a carrot to opt in to restrictions around using them. The carrot ends up pulling from a classic technique of software engineering, encapsulation. Okay. The full power of encapsulation. In traditional encapsulation, programmers make a kind of best effort to hide implementation details from the world around them. Keeping private state private grants the benefits of better code reuse, ease of updating implementation details, and more. But as often is the case, if that kind of rule isn't enforced, over time APIs get designed where internal implementation details leak out. Something very interesting happens if we don't allow this to happen. If an encapsulation can be checked by the compiler and the compiler enforces that no private details leak, we have what you might call full encapsulation. I would just call it compiler enforced encapsulation, but that's just me. These kinds of encapsulations wouldn't allow any aliasing of pointers into them, okay? They'd have their internal pointers fully isolated from the rest of the program, okay? Once we have this, some new capabilities start opening up. We can fence off our shared mutable pointers, making it possible to create single owner encapsulations that can be sent safely between threads. We can lean people in the direction of cleaner API design, as now we have a way to truly keep private implementation details private. We can handle some of the drawbacks of grouped allocations. What kind of drawbacks, you might ask? It's high time we talked about them. Okay, so basically, in their circular linked list example, right? Because we've got this encapsulated in its own system, we're not letting it share, we're not sharing it between threads, right? It's not a thread safe thing to have shared mutable pointers. Duh. So with the compiler enforced encapsulation, and not having multiple threads, right? Right. I think I get it. It's basically then it's up to our logic internally, right? To make sure that it doesn't happen. In other words, you're not going to allow somebody using that data structure um, to update it themselves. It's going to be through like a controlled method. Now, if the logic and the controlled method, just like a safe data structure in Rust, right, that uses unsafe under the hood, if the logic is wrong, then obviously you're going to have UB. But as long as you get that public piece right, the christened piece that you're exposing, then it's safe. I think that's their point. Drawbacks of grouped allocations. If we go back to our earlier example and look carefully, we'll notice something. The question is, what happened to the new stats age 22 allocation? Okay, sure. Remembering that June is a systems language, we can't say the garbage collector handled it because we have no garbage collector. Nor can we say the ref count hit 0, so we reclaimed it, as we don't use ref counting. As a systems language, we can't allow hidden or difficult to predict overhead to happen. Okay, so they're not using ref counts. Obviously, it doesn't have a GC. It's not actually leaked either, as even the memory it occupies will be reclaimed once the entire group is reclaimed. So basically what they're saying, because of the grouped lifetime, right, is that new stats age 22 is still in the employee param lifetime for this particular employee. So this memory is going to be used until this employee is dropped, even though we never actually use this stats allocation with age 22. We only use the stats allocation with age 33. Yeah. For all intents and purposes, though, it's lost to the user until the group is no longer live. It's a kind of memory bloat that happens if we group our allocations. To handle this, we'll need some way of recycling that memory. Yeah, if you did that naively, right? We're going to see maybe they didn't do it naively. We're going to let them cook a little bit, Scott. I say recycling specifically because in June we can't free the memory, as the group is treated together as a single entity where all the allocations in the group are freed at once. If we instead recycle the memory, we can reuse that same memory while the group is live. Techniques to do this have been around for decades, and often people use free lists. Free, unpaid for lists, to keep a list of nodes that have been recycled so they can be reused when the next allocation happens. Oh, that's interesting. So basically so instead of freeing the memory and having to deal with all of that, you would just push that onto a list, right? You'd add, we're no longer using the old stats on this employee, so we're going to push that into a free list. And then the next time we need something, we could check that allocation and reuse it if we want to. Okay, interesting. The problem with free lists is that they aren't safe. If you're not careful, you'll create a security vulnerability and or an incredibly hard bug to find. Yeah, doesn't sound very safe. Instead, we need to build in a safe way of recycling memory into the language. Okay, safe memory recycling. Using the idea of full encapsulation from earlier, we can create fenced-in sets of pointers that we know aren't shared with the rest of the world. Sure. Once we have them, it's possible to track the pointers inside. Okay. So if we have the employee and we know that all of these pointers, including the pointer to the stats object that no longer used, it should just be added to our free list, then we know, again, it's encapsulated, it's fenced in. No other part of the program is going to use this because it's part of our little group. Once we have them, it's possible to track the pointers inside. These pointers can get a copy count, so we know how many copies are live at any point in time. I was about to say, not dissimilar from a ref count, though this has no automatic reclamation. Okay. Once we have a copy count for each internal pointer, we can give developers a built-in recycle command. Okay. Recycling would start at the given pointer and would check the pointers reachable from it. I feel like this is a lot. I mean, I'm going to let it cook a little bit. Right now, I feel like developers having to figure out when to recycle something like that, it's quite a bit of mental overhead. Now, is it less mental overhead than dealing with lifetime annotations? Yeah, maybe. And I guess if you didn't care about the memory bloat, then you wouldn't have to ever use recycle. So we give developers a built-in recycle command. Let x equals new foo recycle x. Recycling would start at the given pointer and would check the pointers reachable from it. Each pointer it finds that it can recycle would go into the safe free list. You might wonder why not do this automatically. There are a couple reasons. The operation is linear time based on your transitively reachable pointers. Yeah, this means you may incur a noticeable overhead when recycling. Because of the first point, it's important to make places where this occurs visible. Good performance to ergonomics trade-off. If this sounds like a kind of manual garbage collection, you're right. My collaborator Jane calls this semi-automatic memory reclamation. You ask once, and when you ask, you get a kind of highly focused mark and sweep for that single pointer, and the pointer's reachable from it. Okay. Yeah. Note this feature is not yet in the reference compiler. We're hoping to implement it in the coming weeks. More work ahead. We have a way of simplifying lifetimes, making for readable code that people from various languages should be able to understand and use. We can also give clear, easy to understand lifetime errors when they arise. Having saved memory recycling gives us a way to keep groups and still offer things like delete in a linked list abstraction. It's convenient, but not so automatic that we lose the visibility into the costs of memory management. That said, there are still some challenges ahead that will need to be solved in the language design and tooling. For example, how do you know when the program is bloating memory? We'll need some way of doing a memory trace when the program is running to detect this and warn the developer. I see this in a way as a more incremental, prototype-friendly way of development. June is always memory safe, but the first version of a program may not be as efficient as it could be in terms of memory usage. Also true in Rust, by the way. If you just clone the shit out of everything, that's one way to go about it. Or put things in ref cells and other smart pointers, right? That's a process we often go through as developers. First, we make it work before we make it good. In June, we keep it lightweight as we keep your program's memory safe, and then we provide tools and support for incrementally improving code. Or at least that's their hope. Future possibilities, relationship to Rust. June has a real opportunity to be a good complement to Rust. Rust's focus on embedded and systems development is a core strength. June, on the other hand, has a lean towards application development with a systems approach. Okay? This lets both coexist and offers safe systems programming to a larger audience. An even better end state requires Rust to have a stable ABI. Once it does, June will be able to call into Rust crates to get the benefits of Rust's substantial crate ecosystem. We're looking forward to collaborating on this in the future. Yeah, this would be really cool. I have thought about like how cool it would be to call Rust from OCaml. But you know, obviously that the stable ABI is important. And it also might be the same thing, or it might not be necessary. The whole OCaml Rust thing that I've been thinking about for, I don't know, ever since I started working with OCaml 6-7 months ago, because they're working on an opt-in GC option for OCaml. So there may be OCaml without garbage collection in the near future. Going beyond OOP. OOP has for decades been the way many applications are written, but it's not without its flaws. Many OOP languages allow programmers to freely break good rules of thumb, like the list const substitution principle, to create a mess of interwoven code between parent and child classes that's difficult to maintain. Okay. So they're basically just like putting down OOP, but not necessarily saying how they're going to fix it. Okay. Exploring related work. Over the years, there have been a number of memory management techniques tried, including many that lie outside of the ones commonly found in languages today. We'd like to explore these more deeply to see which, if any, may help June. Cool. Documentation on the June language and the June reference compiler are now available via the June repo. All right. June repo. And I didn't actually post a link to that article, but here it is. I don't know how they'll prevent the same problem of not calling free in C after allocating it. It's the same problem that Rust is trying to solve using lifetime or C++ using smart pointers. Yeah, sure. You forget to call recycle is the same as forgetting to call free. So they're doing two things though. Like, you only have to care about calling recycle if you want to reuse the memory blocks within that group allocation, right? But once that group goes out of scope, right? Then that group's no longer going to be allocated. So they're still doing the Rust and C++ thing a little bit. Of, like Rust when you don't have to register a lifetime. They're doing that where they have that kind of auto drop behavior, right? So when things are deinitialized, essentially, right? Like the whole, what is it? RAII thing, right? Similar. So I think if I read it right, they're going to be doing both. But essentially, they're not going to free that group until that group's out of scope. And they don't have to think about, Rust is kind of like you have to think about every single individual piece and pointer separately. And this is saying that we can just kind of think of things almost like objects. And then we'd just free all of that at once. So now I don't know. I would assume that that's how they're going to do it. I don't think in your program you'd have to say like recycle employee, like once that function's done. I would imagine that allocation goes away, but we'd just have to see. Yeah, it'll be interesting. Well, it was cool. It was a good read. Glad we did it. Pretty interesting.